Welcome back. This lecture is going to define the system of units we're going to use, and we'll talk about some of the most important properties of fluids. So first of all, we're going to be using two systems of units in this course, and the textbook also uses these same two systems of units. SI, of course, I hope you're all familiar with. That one we won't spend too much time introducing. But the second system of units that we're going to be talking about is British gravitational units. So I've summarized here for mass, length, time, temperature, and force what the fundamental units are. And just to quickly review, in SI, of course, the mass is kilograms, length is meters, time is seconds, temperature, degrees Kelvin, and the force is newtons. Now, the second system of units that our textbook uses is called British gravitational units. And in those units, the mass is the slug, length is a foot, time is seconds, temperature is degrees Rankine, and the force is pounds. So notice this is a little bit different than the system of units that we used in thermodynamics. That was called English engineering units. British gravitational units are actually quite a bit easier to use than English engineering units because they don't have 2 pounds. Instead of using pounds mass and pounds force, they use slugs for mass and pounds for force. So it's quite a bit simpler from that point of view. Now the nice thing about that is that 1 pound force is the force required to accelerate 1 slug at 1 foot per second squared. So that's exactly the same as in SI. 1 newton is the force required to accelerate 1 kilogram at 1 meter per second squared. So there isn't an extra conversion factor in the definition of force like there is in English engineering units, where 1 pound force is defined as 32.2 pounds mass foot per second squared. So really working with British gravitational is the same as working with SI, just with different names for the units. So it's a fair bit easier to work with than English engineering units. Now this would be the system of units that you're familiar with from your first year courses as well. GE 124 and 125 use that same system of units. Now the next thing I want to talk about in this introduction is a concept called field variables. So field variables are variables that are functions of space and time. So that's what they mean by field variables. Some quantity that varies depending on where you are and depending on what time it is. So obviously many things are field variables. So some of the ones that we're going to work with here, we're going to define on this slide. So we have a Cartesian coordinate system here, which defines our position in space. And so some field variables that we're going to work with are pressure is certainly a field variable. As we move around in the room or as time goes by, the pressure can certainly change as a function of where we are and what time it is. And certainly when we're looking at fluids flowing through or over engineering equipment, how the pressure varies from place to place is going to be one of the big things that we're concerned with in this course. Density is also a field variable. Now we mentioned that we're going to be looking at incompressible flows. So the density of our fluids are not going to change as it moves from place to place. Certainly the density will be different in different problems because the fluids will be different in different problems. But the density is not going to change with time. It may change with location. If we have a stratified fluid or something like that, the density might change with where we are, but it's not going to be changing with time like it was in the thermodynamics class. Another important field variable in this course is the velocity field. How the velocity of the fluid changes as we move from place to place, either in internal flows as we go down the pipe or external flows as fluid moves over top of a propeller or airplane wing or something. How the velocity changes with space and time, that's a field variable. Now we'll notice a difference here. These two are scalar properties. Notice they're not vectors, they're scalars, whereas velocity is a vector quantity. So when we're talking about a vector quantity, we need some way to define what direction we're talking about. And so we're going to be using the I, J, and K unit normal vectors that you'll be familiar with from GE 124 and 125. So the direction of our velocities will be specified by those unit normal vectors. So typically the way that that's done is the velocity is broken into three components. U is the component of velocity in the I direction, V is the component of velocity in the J direction, and W is the component of velocity in the K or Z direction. Now, don't get this confused with thermodynamics. U, V, and W are three components of velocity. This is not internal energy, specific volume, and specific work. So don't get the notation between the two courses mixed up. There are three components of velocity. So notice each of these three things will be a function of where we are, x, y, and z, and how much time has passed, t. So each of the components of velocity themselves are also field variables. Next thing we want to look at is some fluid properties that are important in this course. So certainly some of the thermodynamic properties that we talked about last term in thermodynamics are important here. Pressure is a thermodynamic property, and that will be very important in pretty well everything we do in this course. Temperature is important, but not nearly as important as it was in thermodynamics. We're not going to be looking at problems here where the temperature is changing during the problem. We need to know what the temperature is because we need to figure out what the fluid properties are, density, viscosity, that sort of thing. But temperature is not going to be changing as the problem unfolds. Vapor pressure is of relatively minor importance in this course, and that's essentially another word for saturation pressure, the pressure at which the fluid will vaporize. Density, specific weight, and specific gravity are all important properties in this course, so I'm going to be talking more about those in a few moments. Transport properties is another class of properties that are important. The two transport properties that we're showing here are viscosity and thermal conductivity. So viscosity is called a transport property because it governs the transport of momentum in a fluid. Thermal conductivity is called a transport property because it governs the transfer of heat in a material. Now, thermal conductivity is not going to be a concern in this course, certainly is next year when you take your heat transfer class, but viscosity is a very important property in this course, and we're going to be expanding on it later. Now, there are a lot of other properties that may be important in other fluid mechanics courses. For example, surface tension, if we're looking at a two-phase flow where we have gas and liquid flowing at the same time, surface tension becomes an additional property that's very important, but it's not going to be of concern in this course. So the next thing we want to do is take a few of these more important properties and expand on them a little bit. So the first of those is the first one here, pressure. So pressure is a compressive stress in a fluid. And as we just mentioned, it's a field variable. It changes from place to place and potentially with time. So there's our pressure field variable. Pressure, a function of x, y, z, and t. And so if we take a look at a very small element of fluid, a tiny little cube of fluid, the pressure is the compressive stress in that fluid. So we can think of it as a force per unit area pushing normal to the face of all 6 sides of that little cube of fluid. So one of the very first things we're going to be doing in the fluid statics section of the course is figuring out, as we move around in a fluid, how is the pressure going to change? So how is that compressive stress in the fluid change as we move from place to place? We're going to be concerned with that a lot as we move forward here. Temperature, as I said, is a very minor importance in this class, and it's usually constant. Very rare cases where the temperature might change in a problem, but it's going to have a very, very minor role compared to in thermodynamics, certainly. Density is defined as mass per unit volume. Now, in thermodynamics course, we use specific volume all the time. Well, realize that density and specific volume are just the inverse of each other. So density is kilograms per meter cubed in the SI units, or slugs per foot cubed in British gravitational units. So we don't use specific volume really at all in fluid mechanics. Rather, we use density. and they're just the inverse of each other. So if you know one, you can just invert it and you get the other. Specific weight, however, is a new quantity in this course. That's the weight per unit volume. So if we take the density of a substance, rho, and we multiply by g, the acceleration due to gravity, we get the specific weight. And the symbol that's used for that is gamma. So this combination of quantities, density and gravity, appears very, very often, particularly in fluid statics. So sometimes it's more convenient just to talk about the specific weight rather than the density of a fluid. So the units of that, it's a weight per unit volume, so newtons per cubic meter, which can also be written in basic units as kilograms per meter squared second squared, or as slugs per foot squared second squared. The next quantity is specific gravity. And this is a ratio of the density of the substance we're dealing with to the density of a reference substance. So it's a dimensionless number. Specific gravity has no units. So for liquids, which is where we're going to be using specific gravity, the reference substance that is talked about here is water at 20 degrees C. And water at 20 degrees C and atmospheric pressure has a density of 998 kilograms per cubic meters. So specific gravity will be a number which is the density of the substance we're dealing with divided by 998. So the specific gravity of water is 1. Specific gravity of oils, which are a little bit lighter than water, tends to be around 0.8. And of course, there's other substances like mercury that has specific gravity of 13.5. So a dimensionless number that tells us the density of the fluid we're dealing with. Now, the most important of all of these properties, for this course at least, is viscosity. So we want to spend a little bit of time here carefully defining what viscosity is. And we already saw a little bit of an introduction to this when we were talking about Newtonian and non-Newtonian fluids. So the most important transport property in fluid mechanics is viscosity. So let's go back and take a look at this fluid in shear that we talked about when we first introduced the difference between a fluid and a solid. So here's our two plates again. Realize this bottom plate is stationary. That's what the cross-hatching is supposed to indicate there. So we have a stationary plate there, and then some distance away we have a plate that we're going to move to the right by applying a force. Now I defined a coordinate system here, so x is the direction that the plate is going to be moving, and y is a coordinate measuring the location between these two plates. Now notice here we're going to give this top plate a velocity to the right. So we see here our very first velocity field, I guess, and it's the velocity of the plate that we're talking about here. That's what the subscript p is meant to indicate here. So the velocity of this plate is in the I hat direction, meaning that plate is moving purely in the x direction, and the speed that it's moving at is this capital U. So if capital U is 2 meters per second, this plate is moving 2 meters per second to the right, or to the positive I direction. Now again, between these two plates we have our fluid. The distance between these two plates is h. So we're moving this plate at a speed u, and the distance between the two plates is h. Well, if we were to go in here and look at the velocity of the fluid between those plates, for a laminar flow, we would have just a linear variation in velocity from 0 at the bottom plate to u at the top plate, and it would vary linearly between those. So the velocity field, how the velocity varies with position in there, will be given by this equation. So notice here we have our first velocity field for a fluid. Now the velocity is purely in the I hat direction, or in the x direction. It's varying linearly with y. So notice this y tells us how the velocity changes as we move from the bottom to the top. So when y is 0, we're down here and we get 0 velocity. When y is equal to h, then the y and the h cancel and our velocity becomes capital U, the same as the plate velocity. So this is our very first velocity field. It's how the velocity is changing with position in this fluid. Notice this is a steady flow. There's no time in here. This velocity is not changing with time. Now, what we want to do is consider a layer of fluid parallel to the plates. So this little rectangle here is a layer of fluid that we're going to take out and take a look at. So here it is, just expanded. Well, realize that above this layer of fluid, so if we go back to our larger picture here, so above this layer of fluid, the fluid is traveling faster than this layer is. So that means that there's going to be a shear stress applied on the top surface of this layer to the right. Likewise, below that layer of fluid, the fluid is traveling slower than the layer is, so there'll be a shear stress on that layer of fluid to the left. So this layer of fluid is being dragged to the right by a shear force on the top, and it's being dragged to the left by a shear force on the bottom. Now, because this layer of fluid is traveling just at a constant velocity, those stresses are actually equal. So this shear stress, tau, doesn't matter where we go between these two plates, that shear stress, tau, force per unit area, is going to be a constant because the slope is constant. So that shear stress is given by the rate at which the velocity is changing. So let's look at this du dy. So du dy is the rate of change of the u component of velocity, that's in that direction, in the y direction. So du with respect to y. Well, that's constant in this case because we have a straight linear variation of velocity with respect to distance between the plate. Now, the constant of proportionality between that shear stress and du dy is the viscosity. So this is really how viscosity is defined, as the constant of proportionality between shear stress, and this is called the strain rate, du dy. So this is our definition of viscosity. So we'll just state that here. Viscosity is the constant of proportionality between shear rate, du dy, and shear stress, tau, for a Newtonian fluid. So this is another picture of that relationship between shear stress and shear strain rate that we saw in the last video. But now we're identifying the slope of that line, and this is a Newtonian fluid. The slope of that line is the viscosity. So that's how we define viscosity, the slope of shear stress versus shear strain rate. Now, remember that Newtonian means that mu, and mu is the symbol we're using for viscosity, Newtonian means that mu is not a function of du dy. However, remember that it's still a function of pressure and temperature, primarily temperature as it turns out. So if we have fluids at different temperatures, their viscosity is certainly going to be different, but it's not going to be a function of how quickly we strain that fluid. Now, the viscosity we've been talking about so far, mu, is the dynamic viscosity. And if we look at the equation that defines it, we could figure out that its units are Pascal seconds, or if we break this down into fundamental units, it's kilograms per meter second, or in British gravitational, that's slugs per foot second. That's the dynamic viscosity. There is another way that we might find viscosity information given to us, and that's the kinematic viscosity. And that is usually given by the Greek letter nu as opposed to mu. And kinematic viscosity is just defined as dynamic viscosity divided by the density of the fluid. And there is a reason why this is called dynamic and this is called kinematic. I'm not going to go into it too much here, but dynamic viscosity relates shear rate with a shear stress, whereas kinematic viscosity, if we look into it a little bit deeper, relates shear strain rate to an acceleration. So it's just kinematic properties. But the thing you need to be careful about is when you go to look up the viscosity of a fluid to do a problem, make sure you know which one of these you're looking up and make sure you convert it to the one that you actually need if you need to. So in terms of units, kinematic viscosity is meters squared per second, and in British gravitational, feet squared per second. And you can see that if you just put the units of dynamic viscosity in here and the units of density in here. So that's a brief introduction to some of the important properties that we're going to be using in this class. The next section of the course is fluid statics, and so the next video will start to introduce that first major section of the course, fluid statics. We'll see you there.